I was 21, 27 years ago. Over 27 years ago, so. Yeah.
That's not nice.
Not as old as Dr. Roth. Yes.
I'm not gonna pick on Dr. Roth like that.
I pick on Dr. Roth all the time.
How old is Dr. Roth?
You don't have to pick on anyone all the time.
He's 60?
Plus.
You told me he's 6.
He is. He's over 60, correct.
Why is there so much homework in this one?
It's only 10 problems. I counted yesterday.
10?
You're wrong. 1, 2,
There's
3,
8
4,
problems.
5, 6, 7, 8. I was wrong. I didn't count yesterday when you gave me my book. The book though, I was like 1, 2. Oh, I got it.
Oh, do next Friday?
Whoa!
Do this Friday?
Yeah. Oh.
Yeah, let's do this Friday.
Well, you have a test next Friday,
Oh, yeah.
right?
So it is Friday, not Thursday.
Yeah.
So it said Thursday/Friday, so we get to pick.
Yeah, you get a pick.
Okay.
What time do you guys leave on Friday? Because I got classes.
I'll probably take a
Class Friday.
No, we will not have class Friday.
That's a whole. I'll probably
Sorry, 3 hours time slot.
It shouldn't take 3 hours. I did 2, I would do 2.
If you finish within an hour, you get extra.
You get
No.
negative credit. How about that?
Wait, how long?
Just
you
you
get the Friday finishing.
I think 2 would be enough time.
Finishing the classes.
You can do nothing else on a paper. That's fine.
Will we get to use Excel?
Yes.
That was the. Is that it? It made the homework so much easier.
Yeah.
Well, the 6.4-14 was the one that we didn't finish
Well, it's a lot to remember.
for this time, right?
Yes.
'Cause we're gonna finish talking about how to do that today.
I don't know, I really gotta start working on the FM.
Is it supposed to stay back on Friday too?
No, it's just supposed to be cold as all get out.
Okay.
But it's supposed to be back in the 40s by Sunday, so
Because I have to drive to Italy on Friday.
it'll be cold.
I don't know.
Indy's probably gonna get more snow than we are, though. All right. What's that? She heard me? Is that what you said? All right, so.
So turn on your phone there, huh? I'm trying to learn.
All right. So last time we talked about the F distribution, which again is a chi-square divided by its degrees of freedom over another chi-square divided by its degrees of freedom, right? Why I used R and S, I don't know, but that's fine. It doesn't really matter. So we know again that a multiple of the variance, the sample variance, is a chi-squared distribution. So this F distribution helps us get a handle on a ratio of variances. One of the reasons why we're interested in a ratio of variances, again, is because one of the assumptions that we make when doing confidence intervals is that the variances of the two populations are the same. If the populations have the same variances, their ratio of the variances should be 1. So the F distribution is used to help test whether or not that assumption that we make that the variances are the same is a decent assumption to make. Okay. So this is one of the reasons why we care about the F distribution. There are other applications of the F distribution, but this is the first interpretation of why we care about it. It's because we have this assumption that the variances are equal. That's when we use the pooled variance to help us figure out the confidence interval for small samples, for instance. The reason why we pool the variances is because we assume that they're the same. The underlying populations have the same variance. So you do a weighted average of the variances that you got from the sample to help you get a better estimate for what the population variance should be. That's the whole idea. All right, so one of the things that we did in the homework for confidence intervals was, especially for differences and means, was if you looked at the confidence interval and 0 wasn't in the confidence interval, then you could say that there is some sort of substantive difference between the population means, right? Or if we have a 95 or a 99 or a 90% confidence interval, whatever that happens to be, if we have this confidence interval and 0 is not in there, then we're confident that there's some positive, if all the values are positive, or some negative difference between the means, right? There is some difference, meaning that the means really are different from each other. And the way we made that inference was the fact that the 0 wasn't in the confidence interval. It's the same idea here. If we do a confidence interval for this ratio of variances, and 1 is not in the interval, then we're confident that the variances are not the same, right? A ratio of 1 would mean that the variances are the same. So if we get a confidence interval where 1 is not in there, then we're going to be confident that the ratio is not the same, not 1, so the variances are not the same. Which means that that underlying assumption that we had about variances being equal would be not a good one. And you'd have to attack it in a different way. And that's the part that I'm waving off because we're not going to worry about attacking it in a different way for right now. Okay? All right. So we started doing this last time. Pardon me. Same idea. We know that if we want to do a probability that we're in between two numbers is equal to that 1 minus alpha. It's the same way we've set up confidence intervals before. I'm going to put this f random variable in the middle. So I need to make sure I do a ratio of 2 chi-squareds. So for the first one, I did x over y last time, right? I did sx and xy where the x was on top. Okay. I just want to make sure that I do it the same way here. They do it flipped in the book. Looking at the book, they have it flipped. It doesn't matter. It's just, I just want to make sure I'm consistent with what we did with the notes last time. So we had s1 sx squared over sigma x squared over n minus 1. And an m minus 1 sy squared over sigma x, y squared divided by m minus 1. So again, to get the f distribution, I need a chi-squared on top divided out by its degrees of freedom, a chi-squared on bottom divided out by its degrees of freedom. We know that for the sample variance, when I take n minus 1 times the sample variance and divide it by the population variance, I get a chi-squared on n minus 1. So I divide out by its degrees of freedom. Likewise here. Okay. So notice that the n minus 1s and the m minus 1s will go ahead and cancel while we're at it, right? So then we just play the game like we did last time. So I'll have an sx squared over sigma x squared, and sy squared over sigma y squared. And then I want to get the ratio of the population variances in the middle. Well, if I have the rate, I can do the ratio of the y over the ratio of the x for the variances. Then I need to multiply by sy squared over sx squared here. And I need to multiply by sy squared over sx squared here. So everything is in the correct order that we have it. But we need to figure out what the A and the B are, right? Well, the A and the B are going to correspond to the F distribution. Now, before the days of Excel, the F distribution table was ugly. So just to show it to you, here's page 1. Here's page 2. So it's 2 pages. So this is actually a small one. The F distribution table is huge because notice that when I'm doing these, I've got 2 degrees of freedom I have to worry about. I've got a degree of freedom for my y and a degree of freedom for my x. So when you're reading the table for the F distribution, which I didn't bother putting on here because I'm not going to make you do the table. It's not bad to read, it's just I'm not going to make you do it this way. But to do it on the table, across the top are your numerator degrees of freedom, and then down the column is your denominator degrees of freedom. And then you get various F values that correspond to various alpha values. Okay? But here's what is interesting. It only gives you the right tail on here. You don't get a left tail. I need a left and a right tail. Right? Here's how you get those. I'm going to tell you how it works, and then I'm not going to make you do it this way because I'm just going to have you do it on Excel. Okay? But was he born in a barn? All right. So here's the idea. So your F distribution, if you look at a graph of it, they give you by the way, you can see the PDF there on page in the table if you really care. It's got 3 different gamma functions in it, for example. Did you hear me while you were out there?
Yeah, I was listening.
All right. So up and down is what this graph looks like for a PDF, roughly. What was rude? What do you do? Oh, that wasn't very nice of him. All right, so that's what the F distribution looks like. The table gives you values that are over here on this tail. Because the table gives you a 0.05, a 0.025, and a 0.01 over here on the right, which is also very restrictive because you can only do ones that have those particular alpha values, right? Or alpha over 2 values, depending on which way you're looking at it. All right, so again, if I want this to be alpha over 2, to be on this side, then I would need a similar thing over here, right? Just like we've talked about before, correct? Yeah, this left tail isn't given to you in the table. Okay. So here's how you would have to do it. So the notation here, make sure I use the right notation. I want to make sure I use the same notation they do in the book. Huh? You need to know the notation, yes. Okay. So this, just like we have the chi-squared sub whatever, so this would be your F sub alpha over 2. You have 2 different degrees of freedom, so your numerator degrees of freedom, which in this case is the X. Is this backward? That was y over x, and this is x over y. We got to y over x. So this needs to be m minus 1, n minus 1. Nope, backward.
Oh.
I knew it was going to be backward.
What's backward?
This was backward. Okay. Okay, so we notice that. Wait a minute. No, that's right. That's backward. Okay, so in the original, notice that right now I've got an interval that's y over x. That's pinning my ratio of my variances. But that's not how we started, was it? I did x over y, correct? So this is referred to as the numerator degrees of freedom. Oops. But it's where we started, right? It started with the x's, even though when we went through this ratio, we got y's on top. It's still called the numerator degrees of freedom because we started with the x in the numerator, but when we got to the ratio, the x is now on the denominator. It's
So did I thought they got canceled out, like our n-1, like, so how do we?
And it cancels in the formula, but we still have degrees of freedom associated with those distributions. And depending on the distribution, it changes the shape of the F distribution. So this is just a way to keep track of how the shape got changed. So this one is your denominator degrees of freedom. But again, your numerator ends up in the denominator, your denominator ends up in the numerator. It's weird. I agree. It's strange.
Yeah,
I agree. All right.
okay, so
And so this one is you're going to be your F sub 1 minus alpha over 2 of n minus 1, m minus 1.
Why is that weird?
Why is what weird?
Because that.
We call this the numerator degrees of freedom, but when we're doing the confidence interval, your numerator ended up in the denominator.
Well, I mean that. You said you only get the right tail and not the left tail.
So the table doesn't give you the left tail.
Oh, so the notation isn't the weird part.
No, the notation's not the weird part. Here's the weird part. I'm going to show you what the weird part is, and I'm not going to bother showing you where it comes from. It is a nice property of the f function that this turns out to be the reciprocal of this if you flip the degrees of freedom. So the left tail value is the reciprocal of the corresponding right tail value with the degrees of freedom flipped. This is why I'm going to let you use Excel and not have to worry about doing it in the table. Yeah, Michael.
okay, so you can only technically use the right tail.
The table of values only gives you right tail.
Okay,
So to find the left tail, you have to use this relationship in the F distribution. So if you were going to use the table, you would look up the corresponding F value with the numerator and denominator degrees of freedom flipped,
okay.
and then reciprocate it.
So is that still the denominator? That's still the numerator?
This would still be called your numerator and your denominator in the table. You just have to flip it to find the value.
Okay, so if it was 2 and 3, it would be
3, 2, yeah. Yep. It's just the way you would look. It would be the way you would look it up in the table, is all. But we're not going to use the table, so it's kind of irrelevant for what we're doing.
and then
This is for informational purposes only, because I'm not going to have you use the table.
if it was alpha over 2 equals 0.025, you also use 0.025.
You use the same. Yep. You use the same alpha over 2.
Okay.
It's not as bad as it sounds. It's just something else you have to keep track of, and if you've got the tool to figure out the number, why use an outdated table? Yep, same.
So what happens if you special?
Well, they can always be the same. What do you mean, these two values?
Yeah.
Oh, those are different all the time.
They have to.
Oh, no, they don't have to be, but they certainly can be. The N and the M don't have to be the same at all. All right. So let's talk about how we would do this. Let's see, is there one on here? I'll ask you to do 14. Let's do 13, 6.4-13. We'll get into the next section. Ooh. So I need Excel. (6.4-13). Okay. So the values that they give us for the x, there's 8 values for x, and there are 10 values for y. The x values are 15, 23, 12, 18. I typed in 19, 18, 9, 28, 11, and 10.
12.
You realize I'm reading them off the paper, so you saying it's not really going to make me mess up. 20, I can mess up enough on my own. 35, 15, 40, 16, 10, 22, oh, hey. 22, 18, 32. All right, so we came up with the confidence interval that was x or y over x. This problem asks you to do the confidence interval for x over y, which you're going to do it the same way. So since you're doing x over y, you're going to use the y for the numerator degrees of freedom and the x for the denominator degrees of freedom. Right? It's flipped. The problem asks for the confidence interval for x sigma sub x squared over sigma sub y squared, which is flipped from what we developed, right? We developed y over x. Okay? When it was y over x, the x started out on top and the y started out on bottom. Yes? So we would start with the y on top and the x on bottom, which means our degrees of freedom for numerator and denominator get flipped around, is all I'm saying.
Are these variances or?
They're variances, yeah. Okay. So to find the f values, so we've got, just like the other ones, we've got the f dot inverse and the f dot inverse dot right tail. You can use either. Really does not matter. This one's just cumulative probability up to a certain point. This is just probability past a certain point. You'll get the same value either way. So if I use the f dot inverse, I need the left and the right. So this one's asking for a 95%. Oh, it even just says one-sided confidence interval. Let's just do 2 for argument's sake. Two-sided confidence interval, so I'll use 0.025. Degrees of freedom. All right, so this is your numerator degrees of freedom. So we want the y's in this case because we're ending with x over y, so we started with y over x. So this will be your m minus 1, y, the same number of y's minus 1, so it'll be 9. And then 7 for the denominator. So you get the 0.238. I need to zoom in, don't I? Sorry. How many times have I taught with Excel for many of you and still can't remember to zoom in on Excel? What's it? Every time? Yeah, pretty much.
One class. We'll try to do that.
All right, so that's the A value on the left, and then do the same thing. If I do the F dot inverse and use the 0.975 and 9 and 7, 4.82. This is the left, this is the right. This is, oh, you mean there? I used both. I used left tail, but for both of them when I typed it in because I did 0.025 and 0.975. This is the number that's on the left. This is the number that's on the right. Yes.
You said in the table that it reads from right to left.
It reads. It gives you right tail probability.
So does this give you left?
The F dot inverse is you use left tail. Yeah. If you want to use the right tail, you use the other command. If you really want to do it this way, if I do 0.025 and 9 and 7, I get the same value.
Okay, so the 0.2 is like a small chunk.
Yeah. The 0.2 is the x value that's the small chunk on the left.
The 4.8 is like a bracket.
Yeah. That's right. And then this, just to illustrate this one, remember I told you that this should be the reciprocal of the corresponding the corresponding right tail value for the degrees of freedom flipped. So this would be f dot inverse, I'll do the right tail again, of 0.025 of 7 and 9. That would be the flipped around, right? You do get the same value. Look at that. It all works out. That's not our answer. That's the A and B we found. So I still need sample variances here. So this is your A, this is your B. We still need the sample variance for X and the sample variance for Y, right? So here's sample variance for X. Here's sample variance for Y. Oops, so I actually have to type in it. Yeah, I know. I need to put in the command.
That usually helps.
It does, typically. It does usually help. All right, so we're doing X over Y, and I want the confidence interval for X over Y. So your lower bound, yeah, Grace?
Is this the one where we're assuming that the variances are equal?
This is the one where we're trying to see whether or not our assumption that the variances are equal would be a valid assumption to make.
So this will one have to be in our interval?
Yes. Yes, Sam.
What are they?
That's the A and the B that were in the confidence interval that we came up with, yeah. So the formula was the A times the sample variance for X over the sample variance for Y. That'll give us the lower bound. And then the upper bound will be the same formula, just that I use the B. Now again, the reason why I'm doing X over Y is because the problem asked me to do X over Y. So there is our confidence interval for the ratio of the variances. Yes. Yeah, X. Because the problem asks us for X over Y. If we did Y over X, we'd have to flip our degrees of freedom things around. If I did Y over X, then it would start with X on top and Y on bottom, so I'd have to do 7, 9 rather than 9, 7 for the degrees of freedom. Hmm? Well, it's Lincoln's birthday.
It is Lincoln's birthday. I agree about that. It's on my calendar.
Mm-hmm. There's probably someone else's last name of Lincoln whose birthday it is too.
Just true. Poor guy doesn't move the person.
That's true. But you can find one of each.
Totally plausible.
I'm guessing it'll be harder to find the person with the first name of Lincoln than last name of Lincoln. Guessing. With a birthday of February 12th?
No.
Okay.
I can't think of anybody with the last name besides Obama State.
I'm just saying, I'm guessing Lincoln with a surname is a lot more common than a Lincoln with a first name. Anyway, is this okay?
Okay. So the chance of it's equally distributed throughout that interval. So I guess the ratio between the two variances is equally likely to be 0.11 as it is 1, as it is 2.4.
All we can say is that we're confident that the true ratio is somewhere in that interval. And since 1 is in that interval...
Yeah. But you can't say that you're more confident than the interval.
Nope.
We're talking about.
We're just confident that it's somewhere in there. Which is why we're as confident that it's below 1 as it is above 1.
Can you say that one more time? More confident that what?
We're 95%.
We're 95% confident that the ratio of the variances is in between those two values. That's what we're finding a confidence interval here for, is the ratio of the variances.
We don't say anything about one being.
Well, we could say that since 1 is in the interval, the assumption that the population variances, we're confident that you can't even say we're confident. We would say that there's not evidence that suggests that the variances are different. That's what the 1 being in the interval is. Well, because if we're doing this type of inference on small samples, the inference that we typically do involves the assumption that the ratios of the variances are equal. So if we have evidence that the variances are not equal, then we need to be doing something different to do statistical inference. That's the idea. You would want to use a different thing. That's the whole reason why you would do this. So one of the things that you do with models is that there is what's referred to as a global F-test. When you do multiple regression, you get multiple coefficients to different variables. The global F-test is that the likelihood that at least one of those coefficients is non-zero. That's one of the things that you use an F-test for. So you just want to make sure that what you're doing is actually worth the time doing. So if you're doing the statistical inference on these small samples, but even from the small samples, the variances are so far apart that the population variances are unlikely to be equal, then you need to go do something else for statistical inference. You don't want to do a typical one. Yeah, Sam.
So after we find this variance, when we use them, what we say, now we have this.
Usually this is a first step in a statistical analysis, is doing some sort of an F-test to make sure that what you're doing is worth doing. So even though this is the last thing that we've done so far, it's usually the first thing that you would look at from that perspective. When you look at sort of the example I was mentioning with if you're doing multiple regression, the first thing you do is a global F-test. Does it even make sense to do the model it in this way? Am I getting meaningful coefficients to my variables? So that would be the first thing you would even look at. Because if you're not getting meaningful coefficients that mean anything for your model, then you're using the wrong model. So that's what this is telling you.
For part A, we just get faster point estimates, and you're just taking the sample variance.
Yeah, you just do the ratios and variances and call it good. Yep. Yeah, Sam.
So is there a specific set of values that is good or bad?
No, just the fact that 1 is in there is fine. When you're doing the global F test, you would want the F to be large enough past a critical value. But when you're running statistical packages, it gives you the probability that you've got a bad model, essentially. Grace, she's trying to block it.
That's weird.
That hurt my arm.
I said he's trying to block it.
Oh, I thought I heard shit.
Oh, no.
My boy made me nervous. I get nervous now.
I'm waiting for it to whip past my head again.
That's why I'm nervous.
All right. All right. So let's go on to the next section. Talk about another type of confidence interval. What? Dang what?
He's talking about denying throwback.
Oh. Well, mainly I don't want him to knock it into someone else's head.
Well,
All right, so we've talked about confidence intervals for means and differences of means and variances and ratio of variances. We're going to go back to the same type of things that we talked about for the mean, but we're going to do it for population proportions rather than means. So, but the concept will be exactly the same. Yes, Sam.
When you want to watch that video, you can tell about Friday.
Oh yeah, I was going to mention it after I talk about it because it follows this stuff that we're talking about. I recorded a video, I put it on YouTube, I posted it yesterday so it'd be ready, but I don't want you to watch it yet, so I wanted you to do this first. Well, if you subscribe to the YouTube, then it'll probably get a notification.
I don't get notifications. That's also a good idea.
You turn off the notifications or you didn't bother getting on YouTube.
He's not a true fan.
You know what? You're right.
So he's not going to get top fan honors.
That's only say shits.
What if I make a top fan honor? I can give him a certificate.
We got like a
All right.
shout out of the day.
All right. So the confidence, the population proportion idea is, if you're doing polling kind of things, right? Trying to figure out a percentage of a population that has a certain characteristic. Well, if you're going around and saying, for example, you go and survey individual people and say, do you approve of the job the president is doing? That would be a perfectly good example of a type of poll that's done, right? Do you approve, yes or no? Assuming that you're randomly picking people, you assume that the responses are independent. And if you really have a population that's distributed kind of evenly with their beliefs, then you would also have that the percentage should be the same, no matter what. The same probability of picking someone that says yes to that question should be the same, right? So if you want to be confident of what the true proportion is, you set up a confidence interval. Now again, that is a binomial type of experiment, and you're trying to approximate the p. Right? The probability of success of picking someone who approves of the president should be the same if you're randomly selecting the people from the population. Right? So it's a binomial experiment, and you want to try to get an estimate for what that p is. So if you're doing the sampling, then, of course, we know that we can approximate a binomial using a normal if the n is large enough. Right? Where the mean would be n times p. Right? And we also know what the variance is. So we know that if I do y minus n times p over the square root of n times p times 1 minus p, this should be approximately normal with a mean of np and a variance of np times 1 minus p. We agree? That's central limit theorem stuff, right? Okay. Now again, I'm trying to estimate the population proportion. I'm trying to estimate what the p is. That's the population parameter that I'm interested in. Y is just number of successes. If I want to try to get what you think would be a point estimate for p from y, what should we do? If I want to get a point estimate from p, figuring out the number of successes of y, what should I do to figure out a point estimate for p? You should probably do the number of successes over number of trials, right? Y over n. So let's divide top and bottom here by n. I didn't change anything, but I still have a normally distributed variable, don't I? Or approximately normally distributed variable. All I did was divide top and bottom by n. The size of the sample. Yeah.
Then why divide by n because you want to.
That's what I'm trying to estimate what p is.
Okay.
Yeah. So I need a point estimate to start with to be able to get bounds for a confidence interval. Just like what we do with a point estimate for mu, we use x bar. For a point estimate for the variance, we use the sample variance. Same idea. All right. So this is normal, so I can use the same ideas for approximating this like we did for means, right? We did the probability that the difference is less than or equal to some certain value is small, or is large, right? The probability that we're far away is small. We did this exact same setup for means, didn't we? We had x bar here, right? We had x bar here. We had mu here, and we had sigma squared over n here. What?
Absolute
Considering I had no idea what he was asking. Remember, we're doing distance. I want the probability that I'm within a certain range of my population parameter. It's the same concept that we talked about with being for means, right? I want my sample statistic to be within a certain tolerance, or the probability my sample statistic is within some certain tolerance of my actual population parameter. I want that probability to be large, that I'm within that value. But it's the same setup, right? I just did it for population proportions. Well, by the time you go through all the algebra that we did before, I rewrite the absolute value as a double inequality with negative, whatever, and then just move things around. You get this down to that the population parameter should be in between y over n minus the z sub alpha over 2 square root of p times 1 minus p over n. And then the same thing, but with a plus sign. Again, this idea is using the fact that we have an approximately normal distribution. So I'm using the probability, z sub alpha over 2 from the normal distribution table, and then just rearranging things to get to this confidence interval. This is not the only way we could do this, by the way. We could have looked at solving an equation. Solving an inequality. This, if I move the z sub alpha over 2 over to the left-hand side, I could be interested in solving an inequality that we actually have the values being less than or equal to 0, and solving that inequality. We did this idea from the same idea that we did from the normal distribution table. Okay? Now, if we would have done the solving quadratic, or if you square both sides, you can make it a quadratic to get rid of the absolute value sign. If you go through the mean part and do the solve of inequality versus set it up using the normal distribution, you get the exact same interval. For proportions, you don't. You actually get a different confidence interval, different endpoints for your confidence interval, which is what the video is about that I want you to watch for Friday. Okay. It goes through the development of that particular interval. I do ask that you try to follow along. I don't expect you to reproduce what's coming out of that. Okay? Except for the fact that in one of the homework problems you're asked to use this alternative form of the confidence interval, but it's just a matter of plugging things in the formula. So it's not that big a deal. Yeah, Grace?
Why is there a P in the middle and on the side?
Because there would be.
Are they the same P?
Yes.
So how are we going to find one P with...
That's a good question. Very good question. What are you going to do?
I'm asking you that.
We didn't have.
Why should you ask the question?
We didn't have that problem with a. It didn't look like we had that same problem with the confidence intervals, but really there is a mean idea that's on both sides because you're doing the variance, which is in terms of the mean, right? When you calculate the variance, it's distance from the mean, correct? So you really have that same problem. What did we do when we had variance? What did we use? Sample variance. So what do you think we're going to use here to help us get approximations for P? The sample population proportion, right? So this we're going to use the same thing to approximate. So what we'll typically use is what's referred to, they use P hat. So this is your sample proportion, whatever the number of successes is. I probably should use a little y here. So this is number of successes in the sample.
Already?
It is.
We can just keep going. We don't have to go take things to
You know, oh, that's right. You do have a test today.
I forgot.
Maybe Dr. Off realized that.
Okay. I think it started snowing. Shh. All right. So we use the p hat to estimate, or to give us the y over n, but also to estimate what the standard deviation has to be. So that square root of p times 1 minus p over n is your standard deviation calculation for the binomial random variable.
Oh, so it's not just the P.
Yeah, so you'll use p hat to estimate the p, just like you use the s squared to estimate the sigma squared for the confidence interval for the mean.
The P on the inside. That's the population.
Yes, that's a population. That's a population proportion. So, what you're trying when you're doing surveying, you're trying to get a handle on what percentage of the population thinks or wants or believes or what have you. You're not going to be able to survey the entire population. So, from a random sample, you need to get an estimate for what that population proportion is. So that's why we'll use the sample proportion that we get to estimate this for us, because it should be close if the sample size is big enough. That's the idea. All right? We'll do an example of this next time. Watch the video for next time. We'll get through section 6.5, because this is section 6.5. Okay? And then we'll get into section 6.6 on Friday. Have fun on your history and math test. If you're taking a history and math test.
I'm not taking one, but I'll take it anyway.
Okay.
You wouldn't know a single thing. You would